All right, so if you've gotten the chance to get your Cartesian diver working and you've been able to play with it a little bit, meaning you're able to give it a good squeeze and able to get that little diver to move up and down. We're going to take a moment to talk about the principle at work that's allowing this to happen, all right? So we're still on pages 432 through 433, and we're talking about Pascal's principle. Now, this principle is named after the guy who came up with it. He's a guy by the name of Blaise Pascal. This is the same guy that we named our units of pressure after, that is the Pascal, or PA for short, which we talked about in section 1. So when you're calculating pressure, you're going to express that pressure in units of pascals, right? And that's named after this guy, Blaise Pascal. So what's happening here, and what Pascal has to say is that when you exert a force, right, on an enclosed fluid, okay, so what I'm doing is I'm exerting a force on this bottle, and it's important that we note that he says it has to be an enclosed or confined fluid. That's what we have here. So with the top on, this fluid can't go anywhere. I'm exerting a force on it, all right? And what he has to say is that when that force is exerted, the pressure is going to increase throughout the entire fluid, all right? Which means it doesn't really matter where I exert the force on this bottle. I can squeeze it here at the bottom, and I can make my little diver sink. I can squeeze here in the middle, and that gets it to sink, or I can squeeze here at the top. Okay? In other words, it doesn't matter where I'm exerting the force. According to Pascal's principle, the pressure is going to increase everywhere inside the fluid. But it's important to note that he says in an enclosed fluid, meaning if I take the top off of my bottle here and give it a squeeze, that fluid is not confined anymore, and it's just going to go squirting everywhere, all right? So in order for this principle to work, I have to make sure that my fluid is enclosed inside of some sort of system, okay? So when I give it a squeeze, it's going to go up and down. Now, the question we're asking here is, why is that happening? If you're able to, see if you can get your diver, squeeze it just enough, and see if you can get it to just kind of float there in the middle like that. Okay, now if you watch carefully as you squeeze and release, I want you to watch the water level inside your straw. So if you can see that, look very carefully as you're squeezing and releasing. I want you to notice what you can about the water level inside the diver. That's going to give us a hint to what's going on in here. Why it is that by squeezing on this bottle, I'm allowing my little diver to sink and float, all right? Now, what's happening here is actually similar to what we talked about with the way that submarines sink and float. If you look very carefully inside your straw, well, there's a certain amount of water that's being pushed up into the straw. That's because when the straw is underwater, there's a certain amount of fluid pressure pushing into the straw. Now, there's also a certain amount of air that's filling up the rest of the straw. So here we have some water, and here we have some air. Now, the water pressure wants to push up, and the air is pushing back against the water. Now, here's the thing. When I give my diver a squeeze, according to Pascal's principle, what's happening is I am forcing water up into my straw, which means that air is getting compressed, pushed up, and the water level is going to rise. Okay, so when I squeeze on that bottle, it's forcing water up into my diver. It's taking on water, and just like a submarine, when a submarine takes on water, it's increasing its mass. And the same thing is happening with my little diver. When I transmit force into my bottle, it's pushing water up into the straw, and when I do that, I'm increasing the density of the straw. By adding mass, that straw is becoming more dense and sinking. Okay? Now the trick is, and if you're able to do this, you want to be able to release that pressure and let your diver come back up, right? A submarine's no good if it only goes down, right? It has to be able to resurface again. So the question is, how is it that the little diver is able to pop back up to the surface? Okay, well, the answer is, once I release the pressure that's pushing water into the straw, the air that's already in there pushes back, and when I release it, it's going to push the water back out of the straw, which means the water level is going to go back to its original level. The straw is going to go back to its original density. It's lost weight, and therefore it's lost density, or rather, more specifically, it's lost mass. So by pushing water back out of the straw, it's decreasing its mass, decreasing its density, and since it is now less dense, it will float back up to the top, okay? So when I increase the pressure, that's pushing water into the straw, I've increased its density, and now it's more dense and it sinks. When I let up on the pressure, it pushes water out of the straw, and it decreases its density, and it floats. Now, if I can be really cool here, and I want to just increase the density just enough to the perfect point. All right? So basically, if you're a submarine and you sink, you don't want to sink all the way down to the bottom. You want to be able to float at a certain level that's underwater, but not so deep that you're getting crushed. Okay, so that's the talent. If you're a submarine commander, you want to take on just enough water to where your submarine can float at a constant level without sinking down all the way to the depths of the ocean and getting crushed. Okay? So now I want to take some time to talk about how Pascal's principle can be applied to the real world. And for that, we're going to go to page 434, and we're going to look at a diagram that's at the top of the page there. And what you're looking at are what are known as hydraulic systems. A hydraulic system is simply an enclosed system where I have the ability to transmit force from one place to the other. Now, a simple example of a hydraulic system would be like these little syringes that I have hooked up with some piping in between them. So what I can do is I can exert a force on one side of the system, and you notice that force gets transmitted from one part of the system to the other. Now, in this particular hydraulic system, I've got air filling the system. And in certain cases, you'll have a hydraulic system that uses what's called a pneumatic pump. In other words, it's just compressing air and pushing it and forcing it from one place to another. And we'll talk about one of the reasons why air doesn't always work the best in all hydraulic systems. But first, we're just going to look at the math in order to understand the principle of what's going on here. Okay. Now, if you think back to the very first section, one of the things we talked about was a way of calculating pressure, in which pressure is going to equal force divided by area. Okay, and that's what we've got up here on our very first hydraulic system. Now, in this hydraulic system, it's kind of like what I've got right here. All right, both ends of the hydraulic system are exactly the same size. Okay, so let's say I've got a force of 10 newtons, and I'm pushing down on this side of the hydraulic system with 10 newtons of force. We'll say the area of this little piston right here is 5 meters squared. Okay, so thinking back to our formula, pressure equals force over area. If the force is 10 newtons and the area is 5 meters square, then what is the pressure being exerted inside the system? Well, in this case, since we're doing 10 divided by 5, that gives me a pressure of 2 pascals. Okay, meaning, according to Pascal's principle, that pressure is being transmitted from this side of the system to this side of the system. So if I get 10 newtons of force here, that's going to create 2 pascals of pressure, and that's going to transmit it over to the other side. Okay? Now, in this particular case, both sides of the piston are exactly the same size. Okay? Which means the area of the right side is also going to be 5 meters squared. Okay? And in this case, if the area of both sides of the piston are exactly the same, that means that the force I get on the other side is also going to be 10 newtons. In other words, when both pistons are exactly the same size, or both plungers, whatever force goes in, 10 newtons of force goes in, that's going to give me 10 newtons of force out. Okay? And I can show this mathematically. Okay? If I know I've got 10 newtons of force over 5 meters squared, that's going to equal, in this case, I want to know how much force I'm going to be getting on the other side, right? So I'm asking myself, 10 divided by 5, that's going to give me 2. 2 is going to be equal to x over 5. So something divided by 5 is going to give me 2. All right? In this case, it's got to be 10. That's the only thing that could stand in for x. 10 divided by 5 is equal to 2. All right? Now, something really bizarre happens when we look over on this hydraulic system. Now, the only difference between this hydraulic system and this hydraulic system, if you look in the diagram of your book, is one of the pistons has been enlarged. Okay, in other words, it's going to have a greater surface area than the other side of the hydraulic system. And we're going to see what happens to that when I just enlarge the area. Okay, so let's say in this case, I'm exerting the same exact amount of force. Okay, I'm still pushing on this side of the piston with 10 newtons of force. And this plunger is still going to have an area of 5 meters squared, okay? Meaning that pressure that I'm exerting is still going to be 2 pascals of pressure. Over on this side, something weird is going to happen, right? Instead of just getting a 1-to-1 ratio, what's happening is that pressure, since there's now more surface area, is getting exerted. I got 2 pascals of pressure exerted to a greater area. Okay? Let's say in this case, I've doubled the area. The area of this plunger is not 5 meters squared. We'll say it's 10 meters squared. Make that a little easier to read. Okay? So I've got 10 meters squared. The question is going to be, what is now the force that I'm going to get on the other side? All right? So what I can do is I can set up my proportion. If I know I have 10 newtons of force on one side and 5 meters squared of area, on the other side, I've now got 10 meters squared. I want to know what the force is. Okay, well, I divide this out. 10 divided by 5 is 2. Okay, so what this is telling me is something divided by 10 is going to equal 2. Well, the only thing that could fit in for x has to be 20. All right, so basically what's happened here, I've now taken 10 newtons of force and I've turned it into 20 newtons. And all I've done is enlarged the area of this piston over here. This is kind of the basics of how certain hydraulic systems are going to work. Whether we're talking about the hydraulic system in, say, like a hydraulic press, a hydraulic lift, we could be talking about the hydraulic systems that work in your car or in your suspension. Basically what's happening is by putting in just a little bit of force changing the area. If you increase the area, you get a whole lot of force out. So a little bit of force in, a whole lot of force out, okay? That's called a force multiplier. And this is one of the ways that Pascal's principle can be applied and used to our advantage. Just by adding a little bit of force, increasing the area, I get lots of force out. So just to give you another example of how this works, I've set up some real live hydraulic systems here. And what I've done is, you notice that earlier we talked about the fact that if you were to fill a hydraulic system with air, yes, you could transmit force or pressure from one side of the system to the other. One of the problems with air, though, is that it is compressible, all right? Meaning that I can take a certain amount of air that's in this hydraulic system and I can squeeze it into a smaller space, all right? So in other words, I can push on both sides and take that air and compress it, okay? And so it's one of the reasons why in some hydraulic systems, using air isn't going to get you the very best results because I can push down very easily on both sides, and I'm losing some of that force as it's being transmitted. So in this case, I've got a different hydraulic system. This one's not filled with air, but it's filled with water. Now, the thing to understand about water is like most liquids, it's nearly incompressible. In other words, I can't take this water and squeeze it into a smaller space. So as a result, if I push down on this side, it doesn't matter. If I try to squeeze as hard as I can't take that water and squeeze it into a smaller space. And so that force gets very easily transmitted from one side of the system to the other, and not a whole lot of force is lost due to compressing it, right? So liquids, nearly incompressible, which is why they're often used in hydraulic systems like this. Now, just to kind of drive the point home of what we were talking about earlier with the two different hydraulic systems, one with the same area, one with two different surface areas. So what I have here, I've got two different hydraulic systems that are set up with water inside them. And I'm going to test how much force it takes to compress both sides of these hydraulic systems. So I've drilled a little hole in here so I can hook on my force gauge here. And I'm going to go ahead, I'm going to start pulling down. And I can see in order to pull down on this side of the plunger, it's going to take me about 800 newtons of force. All right. So we're going to go on to the other side. And we're going to hook my force gauge on. Now remember, so both these plungers, they're exactly the same size, okay? So kind of like this, both these little syringes, they're exactly the same. So it should require the same amount of force to pull down on it. So we're going to get it to, without twisting it around, all right? Okay, and we're right around 800 newtons of force, okay? So it took 800 newtons of force to push down on this side, 800 newtons of force to push down on this side. And that's going to make sense because both these syringes are exactly the same. So now we're going to go on over to this set of plungers. And if you look carefully, you notice that the other side of the system, I've used a much larger plunger or much larger syringe than on this side, all right? So we're going to see what happens when I increase the size or the surface area of this syringe versus the smaller one. So first I'm just going to test and see how much force it takes to pull down on this side. Okay, so going, pulling, and it looks like, all right, it's right there. We're still at 800 newtons of force in order to pull that down. So now I'm going to try this from the other side. Okay, and we're going to see what kind of result we get. So I pull. All right, so I'm maxing out. I am over the limit, probably somewhere around 1,200 newtons of force. And you can see it's just barely pulling it down. Okay, let's try that one more time. Okay, so over on this side, I'm going to pull it. It's still right around 800 newtons of force. Okay, but if I want to go the other way with the larger piston, try to keep this from twisting itself. Okay, I have to pull with way more force. Okay, and I can even feel it if I were to undo both of these. You can even feel it as you're pushing on one side. If I were to push down on this side, it doesn't take quite as much force, but if I want to go the other way, it takes a whole lot of force to push back, okay? So just by changing the surface area, I've altered the amount of force. If I push on this side with just a little bit of force, I get a whole lot out. If I try to go the other way, I put a whole lot of force in, but I only get a little bit of force out, all right? Which is why I can push down on one side of this with my thumb. I can just put a little bit of force in. I can try to squeeze as hard as I can with this thumb, but there's no way I can stop it from pushing my thumb up. But if I try to go the other way, I can hold this down with this thumb. I can push as hard as I can with this plunger, and this one's not going to go anywhere. Okay, so that's Pascal's principle at work. Either multiplying force, if you go to a larger surface area, a little bit of force in gives you a whole lot of force out.